Okay, guys, we're getting started. All right, fundamental identities. Okay, guys, quiet, please. Oscar, thanks. All right. So this should be pretty straightforward. Now, remember, an identity is exactly what it means. The left side is identical to the right side, right? So, for example, this right here is an identity because the left side is identical to the right side. But if I have something like this here, that's not an identity. And that, in that case, that's just an equation, right? Equation is solved. So some people think, oh, I've seen equal signs in an equation. Yes and no. Yes, if you see an equal sign, it can be an equation. It's an equation if it holds a certain value, but it's an identity when the solution is what? Like for all real numbers, exactly. So this is always true. That second statement, 2 times x minus 3 is 2x minus 6. And the left side identical to the right side. So that's what we call an identity. And that's what we're going to be working with for pretty much this entire unit, to show that the left side and right side are identical. Okay, so just play on words. Some other identities are shown here. Number 4 is definitely an identity. But 3 is an equation, obviously, right? Number 3 is an equation. 1 you can consider to be an identity because it's always true. So that's just a little bit of semantics, right? Now, trig identities, these are the basic ones. You guys should know this. Should be a second nature, especially when you move on to calculus. You can't like think hard, like what's tangent? No, you got to know sine over cosine really fast, right? And remember, tan is y over x in a unit circle. X is cosine, y is sine. We know that. Cotangent is flipped over, right? X over y. And these other ones are reciprocal trig functions like secant, cosecant, cotan, right? We know that. So those should be really easy. Should have those in your back pocket. Some questions, answers on the basic identities. State equals 0 is in a domain of validity of exactly 3 of the basic identities. So yeah, so 0 can't equal 3 of them, right? So which 3 for theta cannot be 0? Definitely cosecant time okay, right? 0 has to get excluded from cosecant because whatever sign it is 0 is 0. We can't move 0. It's also excluded for cotangent, yeah. Yeah, it's also excluded for there. I think that's it. Secant's fine, cosine is fine. Tangent's fine. Yeah, it's like 3 though, I'm a little confused. The sine 0 is 0, tan 0 is 0. Cosine, yeah, I don't know why I said 3. I'm a little confused about that one. A 3 the basic identity. Oh, maybe this one. Let's take it over here. Yeah. Anyway, just know that sometimes 0 has to be excluded. We'll just move on. Okay. Let's just move on to Pythagorean trig identities. So Pythagorean trig identities, you know, a squared plus b squared equals c squared. That's Pythagorean theorem. You know that, right? Or in our case, x squared plus y squared equals 1 squared, right? So what does x represent? Cosine. What does y represent? Sine. So if we substitute cosine squared theta for x squared and sine squared theta for y squared, then what do we get? We get cosine squared theta plus sine squared theta equals 1. Technically speaking, when you write cosine squared theta, it really means this. I think you guys know that, right? Yeah, just don't confuse that, please. Mathematicians are lazy. They don't like writing out bunch of parentheses. So this is valid, but we prefer to write like this. We put the square next to the trig function. We can imply we see it. You know. So anyway. So if you do other exponents, like what if you did like, I mean, this is obviously it's not a true statement I'm writing, but that's the same thing, right? So just so you're aware of that. Okay. There are 2 more trig identities. I sometimes get these mixed up because I don't use them enough. However, you could derive these. How would I take that first one to get the second one here? What would I do to the first identity to get the second one? Audie, go ahead. Totally, 100% correct. So if you're ever stuck on how to derive these, or sorry, if you're ever stuck on recall, how to remember these, that's what I meant to say. you could derive them by simply dividing, because you know one's going to have a tangent involved, right? So if you do that, guess what? And you square true, doing the both sides. Guess what you get? You get tangent squared plus 1 equals secant squared theta. Boom, 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 right? Really easy. And how would I derive the third one from the first one? What would I do to the first one? Yeah, UV's minus 1. Good.
We did do it, but like I just got it.
Yeah, so don't worry if you can't remember. As long as you know the first one, and I'll be honest with you, like I'm 45 years old. I have friends who are in my mid 40s, and we talk about our professions. Some of my friends are like doctors or sales, whatever. They still remember this identity from high school. They still remember this. And they so far moved from teaching math or doing math. So the first one is one of those things you just kind of know. So when I do see a reunion 10 years from now, I'll ask you if you remember this. So just kidding. Actually, there's a reunion tomorrow, so I'll see some of my former students there.
Okay.
125th anniversary of the school. It's crazy. So anyway, you get the same thing.
Where are you?
Okay. So let's simplify. These should be pretty straightforward, and some of the homework. And by the way, the homework will be worksheet style, so you can actually do the homework on the sheets themselves. You don't need extra paper. I made sure things were spaced out, which I also did late last night for you guys too. So I was burning midnight oil. That's my fault. I was watching football and messing around on YouTube. Anyway, so cotangent. Yeah, I know. I started watching movies from like the 80s and 90s. Like, yeah, I don't know why. Yeah. What was I watching? I was watching like Catch Me If You Can with Leonardo DiCaprio. And then I moved on to the Seth Rogen and Captain Heigl films, Knocked Up. I got to that. Then I got back to an Arnold Schwarzenegger film. I was going back and forth. Yeah. Anyway, cotangent. So cotangent's cosine over sine, right? And that's sine. That's just too easy. What's that going to equal, guys? 1. Now, or I could have done this, right? Could I have done this also? I could have done that also. So a couple things I converted. So one rule of thumb when you're doing identities, which I think you guys know, when it is not sine or cosine, make it sine or cosine. That's one technique you could use. That might help. That was my inclination for the first way I did it. We're a cotangent to something in terms of cosine sine, like this with tangent, things cancel, it works out. Or cotangent is right reciprocal tangent. I can do that also. So when I work this out, this is the fun part. Things cancel. So 1 equals 1, check. Or here, these cancel. 1 equals 1, check. So either way, I'm not going to give you that easy on a test, just so you know. It's way too easy. Yes. A question? Oh, okay. Okay, number 2 is a little bit more intricate, but it's not too bad. Sometimes it might help. I think you guys know that there's going to be a 1 in the numerator, but sometimes it helps to have some of the trig functions in close proximity so you can kind of see what's going to happen. Because what's sine squared plus cosine squared? 1, right?
No, 1 plus tan squared is
Secant squared, which again, if you forget, you can always derive it. But it's secant squared x over secant x. And then that's just secant x straight up. And remember, simplify exactly what it means, right? Why make it look simple? That looks complicated. That looks simple.
So when you simplify, like obviously there's like some x's that
state the domain. Don't worry about that. I mean, of course, we have to realize that x can't be pi over 2. But don't worry about it. Yeah, that's fine. I mean, if you're solving, yes, or if you're doing like some sort of interval, but yeah. Okay, easy peasy. Okay, co-function identities. Now the word co actually is short for complement. Actually, I didn't know that until a few years into teaching. It's actually short for complement because cosine
complement.
of sine. And what's meant by that? For example, the cosine of 60 degrees equals the sine of 30 degrees. That's a true statement, right? Because sine 30 degrees is 1/2, cosine 60 degrees is also 1/2. And 60 and 30 add up to 90. So this will always be true. So I did like, I guess it was really weird, like, hey, cosine like 48.7 degrees. I know it's going to equal sine of 41.3 degrees. Why? I know it's 40.7 plus 41.3 adds up to 90. So that's always going to be true. And that's also because where do they come from? They come from a right triangle, right? Angle A plus angle B clearly add up to 90, right? Angle A plus angle B clearly add up to 90 degrees, or pi over 2. So guess what? B will be 90 minus A will be 90 minus A. So we know it's all going to work out just fine. So I don't know if we necessarily have to go through this derivation. I'll just give you the identity straight up. Yeah, I don't think we have to go through this derivation. I think do you guys get the idea? Yeah, so just know this. So we could just kind of just cross this off. Just know it. So those make sense. And likewise for cotan, tan, cosecant, secant. So cotan is a complement of tan, cosecant is a complement of secant. So we should be fine there. Okay, even odd. That comes from unit circle. So say you have a theta like this, right? And then say you got negative theta. It's pretty clear that cosine theta is going to equal cosine negative theta. Right? Because if I did 30 degrees, cosine 30 is positive because negative is still positive. The exponents. So there's going to be that symmetry. So that's an even symmetry. So this is an even symmetry. However, if I switch this to sine in the fourth quadrant is negative, right? So if I do sine negative theta, it's going to equal negative sine theta on the other side. So that's an odd symmetry. Likewise, a tangent. So think about the unit circle, right? If you go like 30 degrees, the tangent here is positive, and negative, likewise with sine. So those are also just think about unit circle. That's pretty easy. So now we can actually do some examples, and then we'll go back to simplifying again. That's if cosine theta equals 0.34, that just equals cosine theta, which equals 0.34. Here, it's a complement, right? However, we got to write like this first. Because what do we assume theta is here? How we're solving this. But if you were cosine 0.34, theta would be what quadrants? 1, which means it's the cubes, which means less than 90. So I do, and then acute angle minus pi over 2. The acute angle of that minus pi over 2 is negative, right? So that's why I reversed it. I reversed it to make it like that, which now I know is -1 times sine pi over 2 minus theta. And what's pi over 2 minus theta? What's that identity? It'll be cosine theta. So it's -1 times cosine theta. So the answer is negative 0.34. A little more drawn out, but I want to make sure you guys see why that's true. So because that's reversed. So when that's reversed, that makes it a negative, right? Or you could reverse on the inside, but it's still could negative outside. Okay, questions so far? All right. No, because if we go look at up above, pi over 2 minus theta is cosine theta, but if you reverse this, then there's a negative on the inside. Yeah. And we have cosine negative angle, it makes it a negative sign. Oh, that's why.
But then the identity up here says like it's an even function, right?
For cosine, but not for sine. We're working on sine right now. We're working on sine. Sine's an odd function. Because that's what you're starting with. No, we're using cosine theta as substitute at the end, but what we're starting with is an odd function. Okay, and let me just look at timing, make sure I don't mess up timing here. We are going till what time? Gosh, almost October. 10:05. Okay, we're doing well. Okay, let's keep moving, guys. All right, simplifying. Again, consider factoring. Factoring's huge. You made it this far. You guys should be fine at factoring. Fractions, be comfortable with fractions, especially conjugates. Might have to consider that, just to kind of get things to cancel out nicely. Maybe you might have to expand a FOIL, perhaps. Sometimes expand FOIL actually is detrimental, could be counterproductive. So be mindful about that too. So for examples 4, 5, 6, 7, 8. So what I'll do is let me do let me do maybe 7 and 8. Let me do the harder ones. And I'll guess I try 4, 5, 6. And then we'll solve after that. So let's do 7. So what's the LCD here, guys?
1 sine squared.
Yeah, totally right. So you gotta multiply the top by what it's missing, top and bottom by what it's missing. So you gotta do 1 plus sine x to both top and bottom of the first fraction. And top bottom of the second fraction by 1 minus sine x. And if I do that correctly, I should get this up top. And down below, I should get this, right? Okay. Here's the fun part. What crosses off?
The top is just 2.
Top is just 2.
The bottom is.
And down below is 1 minus sine squared x.
So sine squared.
Yeah, and that's using a trig identity. That's an extension of the Pythagorean trig identity, right? Because we know, right? We know that if sine squared x plus cosine squared x equals 1, and if I were to isolate cosine squared x, it's 1 minus sine squared x. So there we go. So 2 over cosine squared x. I'm still not out of the woods yet. I can still simplify a bit more. What can you say after that? 2 secant squared x. Now, what I probably would wind up doing on a test for this kind of question, because it can be kind of vague, like, hey, when do I stop? How do I know I'm done? I think I'd probably make some multiple choice question, where I probably would say, here's what you got, here's our 4 choices. Yeah, still got some more. But I think that's what I would do. I'd probably make a multiple choice question. So that way you're kind of forced to see which one is going to make sense. Audie, go ahead.
So, what was on like last year was like, I think this one will like do the expression and make it equal to the solution.
That's an identity. We're not there yet.
Oh,
These are just simplifying.
so it's just
This is I'm just doing the building blocks right now. Yeah, the identity. Yeah, no. So that's when you have the identity given to you. You have to verify it. We're not there yet. But we will get there. That's really the majority of what we'll do. This is just the beginning stuff. But yeah, totally. Okay, let's talk about 8. You're going to want to probably do the conjugate. If it's an identity, I think it's more obvious what you have to do, because you have to make one side look like the other side. But one technique that's good is using the conjugate, because if you do that, then the bottom comes out pretty clean. You might be on this on the bottom. And up top, I wouldn't simplify just yet. Or sorry, I wouldn't distribute just yet. What does that bottom become? Yeah, it does. Yeah, because if you derive it from the sine squared plus cosine squared divided by cosine, yeah. So the bottom will be tan squared x. And the top is tangent squared x still. But the tan squared x is canceled, right? Boom, boom. Secant x minus 1. Yep, very nice. Okay. All right, why don't you guys try 4, 5, 6? I'll give you guys about 6 minutes. I think you just need a couple minutes for each one. I'm gonna freeze my screen and do as well, and then we'll compare.
Yeah, no, it's tan squared over sine squared. Yeah. 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 This one's the easiest thing ever. You can't get that into.
I don't remember the identity.
No, there's no identity. That's it.
Electrons turn.
What?
Okay, let me know when you guys are done.
With 4 and 5. This week, right after that, you get X plus 2.
See how I do that though? Like,
No, why? Like I don't understand what I
accidentally do it. Because tangent square. All square. Got it.
All good.
You guys should get sine x for the first one. That's pretty easy. Second one, you get sec squared x minus 1 up top, and sine squared x on the bottom. Then you convert. You get tan squared x in the numerator. Convert more. Tan squared is sine squared cosine squared. More sine squared moves off to the side. Use cross off. More cosine squared x. That is equals. That should be pretty simple. Okay, let's keep on moving. And example 6, I think if you guys are still working on it, I'll freeze my screen one more time. Let's work on example 6. We need factor.
Right. So I might have done something.
Well, sine can't be 0. It's just like pi.
Okay, that should be pretty easy. Example 6, guys. We good? Yeah. Okay. Cool. All right, let's keep moving.
Yeah, but think about how.
All right, guys, quiet down. We're going back to me talking. Thanks. And you guys can chat away. So we got examples 9, 10, 11, 12. Let me, and 13. Let me do a couple of these here and I'll have you guys try some. So solving, so this is what I should have done on the test. It's really more clear if I want a general solution or a specific domain. Here we have a specific domain to find the answers, right? So we got to find between 0 and 2 pi not included, 0 is included. So what I would probably do is I'd probably multiply both sides by sine x and convert cotan to cosine x over sine x. It's probably the first thing I'd do, right? So I did two things at once. I changed the cotangent to cosine over sine and multiplied both sides by sine. Then these cancel. And what do you want to do next after that?
Figure out when cosine cubed is equal to cosine.
Yeah, so collect all terms on one side, correct? And then factor out. So it's pretty clear you got two things to work out. Cosine x equals 0 or cosine squared x minus 1 equals 0. So using zero product property. So that would be where at pi over 2 and 3 pi over 2?
Yeah. Yeah. Yeah.
And that would be at 0 and pi.
But then the sine, yeah, sine's on the bottom.
Wait, did I make a mistake?
No,
So that works, but then like
sine
sine's
can't.
on the bottom.
Sine can't.
Oh, right, yes. So right, no, you're correct. We do have to exclude. You're 100% correct. We can't divide by 0, so you're going to exclude these two. Right. So you do have to check your work also.
Oh, we get sine theta, sine zero.
That is correct. Check for extraneous solutions. Yeah, because you can't, and cotangent of pi over 2 is okay, because that's x over y. That's fine, as well as 3 pi over 2. Yeah, and also cotangent of 0 and pi is not okay. So, yep. Like, here's the extraneous solutions.
No, he just got no solution. Wouldn't we just divide instead of subtracting, like divide both sides by cosine x instead of being like cosine?
If you do that, you lose a solution.
Yeah, no, I lost the solution.
Yeah, I wouldn't do that. Yeah. Okay.
Because it's divided, that's zero.
Let me do,
Those are the solutions.
let me do, example 11. And I'll have you guys do 10, 12, 13. Okay, I'm gonna jump to example 11. I would do this, guys. Let some random letter like A equal cosine x.
Oh yeah, I remember the.
So you do this, guys. Guys, quiet, please. Thank you. When you factor, you should get 2a and a, and then plus 2 negative 1. Is that right? Yep. So 2a minus 1 equals 0. Or a plus 2 equals 0. So a equals negative 2. Or a equals half. Now I bring the cosine back in. But this is going to be no solution because cosine cannot be negative 2. And that would be pi over 3 and 5 pi over 3. And I think that should work out fine.
If you want to factor it, cosine, totally fine. I like to sometimes use another variable as a bridge, just to make the math look a little cleaner. It's up to you. You could keep cosine in the form cosine, factor it like that. But it is a quadratic, right? So you got factor in quadratic. And when I factor it correctly, I got that. A is 1/2, A is -2. But 1 is going to be not good. You can't, cosine can't be -2. But cosine could be 1/2, and I find that it's good.
You have to do like plus 2 by take both of this is final solutions.
You are correct. You're correct. You're correct.
Thank you, dude. Yeah, I thought it was from 0 to 2 pi. So pi over 3. Yeah, sorry, I was doing this the 5 from 0 to 2 pi. I didn't realize that's for all. Yeah. Okay. Why don't you guys try 10, 12, and 13? And we'll wrap up the notes. Try 10, 12, 13, guys. And by the way, don't divide the tan. Example 10. Don't divide the tan.
If you count for the solution, can you divide 10 by 10?
When we
When
count.
tangent x is 0, as a solution, then can I divide it?
Yeah, you could, sure. Yeah, because then you've already taken care of it. Sure.
So we got pi over 2. We got 3 pi. I think it's just in 5.
Yeah.
Yeah. Just pi over 2. I think cosine squared x.
Cosine squared is 1 minus sin squared.
Yeah.
Okay, so that's what I got for number 10.
I think K pi is an integer, and then the other one pi over 4 plus 2 pi k, 3 pi over 4 plus 2 pi k. I don't think it's all that close to it. Okay, then.
Okay. Okay, I'll leave it up for a little bit. Go and work on 10, 12, and 13. I'll just read my screen and work on 12 and 13.
I know you are. Yeah. You already do it. Yeah. You don't have to do this out because you already did it. What's the 9 there? Was that a comment? Really? Really? I am not there. How's it going? Oh, yeah.
Well, all we have is native, who's saying I'm scared to go to all the time.
Wait. This is why I got 5.5 on no cap. Awesome. Yeah. So sign has to be YouTube too. Yeah. Or just one.
I hope you can use the red abstract.
So I would for it. I would for it. Well, just power 4 plus 5k, right? Nope, that's totally wrong. That is insanely wrong. What positive 4 plus 5k plus? Yeah. Yeah. That's an Oscar. See, we both made the same. Probably could. It's a really easy mistake.
And this would be.
Yeah.
It's a different question.
So then would it be hard to?
Yeah, I know, we just had. I like to start. I know, I'm sorry. You're the twice reaction, right? I did.
I'll never forget.
You did that too. That works all. For that. You could always work using.
Where is it? Isn't
I'm
it
gonna
like
pay that.
No, no.
Okay, here's the answer for 12 and 13. They're on the board. For 12, we got pi over 2, 3 pi over 2. So 13, we have pi over 6 plus 2 pi k, pi over 6 plus 2 pi k.
And I think that is that. Okay, so we're all done with notes today. I'm very happy we got part 1 done and we have some time spare. So if you want to get a head start on homework, you may. Homework is that other packet I just gave you guys. And simply, it should be very obvious. It's just homework 13 handout, all the problems on the first 2 pages. There you go. Should be very straightforward. You're doing the first 2 pages, 1 to 10 all. So, yep, that's it.
Test questions if you don't mind.
Yeah, I'll come back. Yeah, if I need to update your test, I'll come take a gander.
Do you want me to like give this to you?
I already took care of it. You're updated.
I'm not actually wrong. I'm maybe like Jamar. He did good.
Chase is going to kill this weekend.
Really?
Play Tennessee. Tennessee cannot defend.
I need Jamar Chase VR.
Jamar Chase. Yeah, 20 yards. That's my bad.
What's your thoughts on Zach's mobs?
I like him too.
I should put them in?
Totally.
Yes.
Totally.
Should I put him in?
He's getting so many touches. And Richardson back too. So Richardson will. I don't think they're gonna have Richardson run around too much because he has a concussion. So I think it'll probably give it Moss more than goal line,
Okay.
but I love Moss.
Should I put him in for Stephon Diggs?
Oh, no, you gotta play Diggs.
Okay. Jalen Waddle.
Gotta play Waddle.
Okay. Calvin Ridley. I'm not taking him out.
Yeah.
And then Jerome Ford.
Yeah, you like a team. I think you're already late. Okay.
I'm 0-3.
I think it's point folks team Ford and Moss. I mean, Baltimore's run defense is not great. Ford's gonna lot. I mean, Kareem Hunt's fast, but Kareem Hunt you only have like 5 carries for 50 yards. I think.
No, I'm not.
This guy's doing a lot of research last night. And all these stats really well. Moss is getting a lot of. Moss doesn't have to share the ball with everybody. And it's back in Indianapolis where they tend to play fast. So the pace might work. Here's the thing to think about too. Actually, this is why
Zach Moss is averaging 21 points.
That's why I go Moss. The offensive coordinator, so the head coach for Indianapolis was the offensive coordinator for Philadelphia last 2 years. Still has that easy to run offense. But he loves running the ball. So when he has Anthony Richardson, he's thinking, so I got another deal on Hurts. So much bigger. Because Anthony Richardson's a big dude, like 6'4", 240 pounds. So he likes to run the ball. The head coach of Indianapolis. So Cleveland does too, but it's a visual game too, so it might be a little tighter. Those are good receivers. I keep all those receivers out.
I thought I think they were the same thing.
Same. I thought they were.
Oh,
Yeah, I'm sure I might get 4 there.
I took my.
I did not.
Oh, my bad. What about, could I put him in for Alexander Madison?
I went to him. Only thing is because now Cam Akers can play. Cam Akers, he's the other running back that Minnesota picked up. Also, it's in Carolina, but the Minnesota defense is so bad that my guess is going to be another shootout. So Minnesota's going to be, if Minnesota finds itself in a deficit, they're going to start passing more instead of running. So it kind of takes Madison's
So I should sub
usage.
Madison out.
I'll sub Madison out.
Thank you.
Actually, in that case, I'll play both Ford and Moss.
Yeah, I'm putting
Yeah.
Moss in for Madison.
Yeah, I'll get Madison out of there.
All right, thank you.
Yeah.
I'm gonna be honest with you. What? It doesn't add to your points.
They suck.
No, you don't have points from your bench.
They won a Super Bowl. They went down the hill.
We should add another running back spot.
That's
We
the
should
second
add
one,
another
very
running back
bad.
spot.
And the rest like downhill.
Another flex spot.
Dude, that is low as you can go at this point. Yeah, but you're right. After like.
Mine was like, do not play Dijon no matter what. And then he offered me a trade for Dijon, like 2 days later, like, take it.